Okay. Good afternoon, guys. Okay. Yeah. So I know some of you probably noticed. I'm not sure if you get a notification when I finish marking, but in case you don't know, I finished marking the coursework, and then but I still have to upload solutions to the coursework, which I will do today. Okay, so look out for these things today. Look out for solutions to the exam. And also I owe you assignment 5, which I will work on and post for you today as well. Okay. In this meeting today, what I want to work on, solvable groups. And also introduce our kind of like the next part of the course, which is rings. We'll just get started with rings and fields, which is kind of like the next part. Okay. And just like last week, my goal is to stop about 10 minutes early and give you a chance to give you time to fill out a questionnaire, which I'll post a link to it in the chat. And I will try my best to do it so that it's not rushed at all. Okay. Okay. Oh yeah, I'll also say if there's if you're not sure about how the assignment was marked, or like if I added something wrong, you can just send me an email about that. Okay. Yep. Right now we're talking about solvable groups. To talk about solvable groups, we need to talk about normal series, right? So I need to remind you, what is a normal series? Okay. A G be a group. A normal series for G. Okay. It's just a kind of a sequence of subgroups of G, starting at the top with G, and then G1 is normal in G, G2 is normal in G1, and all the way up to Gn, which is the trivial group. Okay, and this series Okay, a normal series for G, which is this, and this normal series is called abelian. This normal series is called abelian. Well, if each quotient of the bigger group by the next smaller group is abelian. So if G0 mod G1, G1 mod G2, so on, all the way up to Gn minus 1 mod Gn are abelian. And it's called cyclic. Well, you can guess if these quotients are all cyclic. Oops, I didn't realize I didn't have enough from there. Yeah, so it's called cyclic if G0 mod G1 is cyclic, G1 mod G2 is cyclic, Gn minus 1 mod Gn are all cyclic. Okay. Then that's what an abelian series is and a normal series is. And then we have the definition of solvable. Okay. G is called solvable if there exists an abelian series, an abelian normal series for G for some n. Good. That's what it means to be solvable. Okay, and what's an example of a solvable group? Well, any abelian group is solvable. Let's see why. Let's take an abelian group. Then A is solvable. Well, to see why, just write down the series. This is a normal series for A, and the quotient A mod the trivial subgroup is abelian because it's just A. This is an abelian series for A. Okay. So any abelian group is a solvable group. Okay. Of course, that's not the only thing that can be solvable. Another example. Let P be a prime, and let G be a P group. Then G is solvable. Okay, let's see why. Sorry, okay. Let's show that G is P group is solvable. We need to remember for this, we need to remember that if G is a P group, then the center of G is non-trivial. So with that in mind, okay. So now our proof goes by induction on the order of G. Okay. So let the order of G be P to the N for some N greater than or equal to 0. And then we proceed by induction on N, the exponent. So if N equals 0 or 1, then G is either trivial or a cyclic group of order P. Okay, and both of these are solvable. Both of these are abelian groups, so solvable. Okay. So the base case is no problem. Now assume any groups of order P to the 0, P to the 1, P squared, all the way up to P to the N are solvable. Assume all groups of order up to there are solvable. And let G be a group of order P to the N plus 1. Okay, I see this request. Okay, I hope that's good now. Okay. Right, so basically we're doing this by strong induction, you know. Assume any group that has these orders is solvable, and we're going to show a group that has one more P in it is solvable too, like P to the N plus 1 instead of P to the N. Okay, and we need to use the fact that the center is non-trivial. Okay. So the order of G is P to the N plus 1. The center of G is non-trivial. So let G bar be G mod the center of G. And now this is a group. Well, since the center of G is non-trivial, it doesn't have order 1. It has to have order P or P squared or something like that. Okay. Oh, I went too far there. Okay, I think that's hopefully good. So the set order of the center of G is either P or maybe P squared, or maybe it could be P to the N plus 1. If it was P to the N plus 1, that would mean that the center of G was all of G, so G would be abelian, we'd be done. So it's probably not that, it's somewhere in there, right? Okay, but the order of G bar, which is, the order of G mod the center of G. Well, that's just the order of G divided by the order of the center of G. It's P to the n plus 1 divided by like some P to the J, where J is between 1 and n plus 1. In other words, this is less than or equal to P to the n. Okay, and now our induction hypothesis tells us that G bar is solvable. Okay, G bar is solvable by induction hypothesis. Well, let's write down our abelian series for G bar. So G bar equals G0 bar, and G1 bar is normal in that, and G2 bar is normal in that, and so on until Gn bar is a trivial subgroup. Okay, but remember G bar, this is G mod the center of G, and a normal subgroup of G mod the center of G corresponds to a normal subgroup of G which contains the center. Okay, so there exists G1, a normal oops, that was the wrong way. G1, a normal subgroup of G where the center of G is contained in G1. Okay, there exists and then there's a normal subgroup G2 of G1, which contains the center of G. Oops, this is G0. And again, center of G is contained in G2. Okay, and then G3 bar is a normal subgroup of G2. So there has to be a subgroup, like a normal subgroup G3 and G2 containing the center. So this is by I'll just say by the isomorphism theorems. Well, we can say that we have a normal series like this. Well, G0 is at the top, and then we have a normal subgroup G1 and a normal subgroup G2 corresponding to G2 bar, and then all the way down to Gn, and Gn corresponds to the center of G. Okay. Not only that, but we also know that G0 mod G1 is going to be isomorphic to G0 bar mod G1 bar. Okay, also, G0 mod G1 is isomorphic to G0 mod the center of G divided by G1 mod the center of G. This is the third isomorphism theorem. Same for G1 mod G2. And all the quotients are like that. So G0 mod G1 is isomorphic to G0 bar mod G1 bar. And our assumption is that these quotients are all abelian. So these quotients are all abelian. So therefore, G0 mod G1, G1 mod G2, all the way down to Gn minus 1 mod the center of G are abelian, but the center of G is abelian too. So the center of G mod the trivial subgroup is abelian. Oh, I went off a little bit again, sorry. Okay, the center of G is abelian. So now if I just add on to the end the trivial subgroup, I have an abelian series for G. In other words, G is solvable. So G is solvable. So that was the induction step. So that completes the induction step. So I guess we'll say completing the induction step. Oh, can I explain over? Yes, I can. Okay. So let's go over the information we have. We are, by our induction hypothesis, we have that each quotient is abelian in this series. So G0 bar mod G1 bar, G1 bar mod G2 bar. And then using the correspondence, so each bar, like G0 bar corresponds to G mod the center of G. G1 bar corresponds to a subgroup G1, and then G1. Oh yeah, let me remind you. Yeah, so like here part of this theorem is that you corresponding to G1 bar, there's a subgroup G1 where G1 bar is just G1 mod the center of G. Okay, so we're able to take each of these subgroups of G mod the center of G and lift it up to a subgroup of G containing the center. Okay. This might be, I guess, is what confusing you, that I did not write this down. That's really my fault. Sorry about that. Anyway, so you also have G2 bar. That's just G2 mod the center of G, and all the way down. So each of these bar subgroups corresponds to a subgroup of G containing the center. Okay. And so now, when I look at G0 mod G1, the third isomorphism theorem tells us that's isomorphic to G0 mod the center mod G1 mod the center. And this is G0 bar, this is G1 bar. And our assumption is that G0 bar mod G1 bar is abelian. So that tells us G0 mod G1 is also abelian. And we do the same thing for each quotient. So each of these quotients is abelian, and the center, the bottom term, is also an abelian group. So that tells us that this, if we look at this whole thing now, it's the quotient of each group, each subgroup by the next one down is always abelian. So that gives us an abelian series. In other words, that tells us that G is solvable. Okay. And that completes the induction step. Okay. Does that answer? Is that explanation helpful, or should I? Oh, why is it? Oh yeah, sorry. So it should be Gn minus 1 mod Gn, but just okay, so if I look at the top one, the bottom term of the top one is Gn bar is the trivial subgroup. Okay. So according to this theorem, that means we should have a subgroup of G containing the center such that Gn mod the center is trivial. We just take, that just means Gn is the center, right? So then if we look at Gn mod the center, it's just center mod center, which is trivial. Okay, so Gn bar is just the center of G, while the center of G, that's just another way, that's the trivial group. Okay, so here, maybe it's this, the center is also, it's just Gn. Okay, and then here we just take this to be Gn plus 1, I guess. Okay. Okay. But yes, thank you for that question. I'm not sure if I said it or not, but I definitely didn't write that each of these Gn bars corresponds to Gn mod the center. Okay, which was the whole point. So if we accept all that, now we have proved that, well, we've completed the induction step. So now by induction, all P groups are solvable. All P groups are solvable. Okay. So solvable groups like includes a lot of different things. You know, so for example, this tells us a lot of different things are solvable. Q, quaternions, D4. Those are just some two groups. Those are both solvable. As another example, we have this subgroup, we have this group H. Okay, this is actually solvable. Right? What is the reason for that? Okay, well, look at, in the assignment, we showed that, well, we either showed that I think in the assignment we looked at the center of H, but then as an example in class, we looked at H prime. So one way or the other, we saw that H prime is a set of all matrices that look like this. Okay. Now, this is an abelian group. H prime is abelian. To see that, well, we can deduce that from facts we already know, because we know that H prime is actually equal to the center of H. The center is always an abelian group. So H prime is abelian. Now we look at this series for H. Okay. Now we have this normal series for H. Now H mod H prime is abelian, because that is true for whatever group I have. You know, if I take any group G, G mod the commutator of G is abelian. That's kind of the point of the commutator. Okay, so H mod H prime is abelian. H prime is also abelian in this specific case, not in general. But here, H prime is abelian too. So now this tells me gives me an abelian normal series for H, so H is solvable. Okay. And this kind of suggests kind of a way to find out if a group is solvable. Just look at the commutator and see if that helps. So we get that leads us to a definition. Okay. The derived series of G is defined to be start with G, then G prime, then G prime prime. In other words, the commutator of the commutator, and G prime prime prime, and so on. And in general, we might do like, and G n with brackets means n primes on the top. Keep on going. That is called the derived series. Okay. Then proposition. If G to the n is trivial for some n, then G is solvable. And the proof of this is very fast. Look at this, look at the derived series. By assumption, this G to the n is just a trivial group. And also G mod G prime is abelian. G prime mod G prime prime is abelian because it's of the form a group, some group mod by its commutator. G prime prime mod G prime prime prime, that's also abelian. And the only fact we need to know is that for any group, what's another name for a group? For any group K, K mod K prime is abelian. That's the property we're using. Okay, a group mod out by its commutator is abelian, and so each of these quotients is always abelian, and so therefore therefore G is solvable. So we have dots and then G is solvable. Okay. Okay, so now let us take a break until 12:45. Then we'll kind of finish up talking about solvable groups, and then in the last part, we will start talking about rings, at least for a little bit. Okay, so yes, see you in about 8 minutes or so.